Alright, so you guys had to attempt that worksheet on polarity of bonding. I know it was a bit challenging, especially when it came to writing the Lewis dot structures of different molecules. So I'm going to do a little video tutorial here on how to think through those problems, because you'll need to be able to do them on the next exam and for the rest of your life. So we'll take a first example, and then I'm going to give you guys some pointers on how to find a few shortcuts that can help you make these problems a little bit easier. So let's take the example of one of the first ones on the worksheet, where you were asked if calcium and chlorine were to come together, what kind of a bond would they form? And I'm sure you guys know at this point, at least, what you need to do first to figure out what kind of bond they're going to form is to figure out where is the power imbalance. So who's stronger when it comes to pulling electrons toward themselves. So in this case, there's kind of two things you need to know about a particular atom to try to figure out what it's going to do when it meets another atom. So you need to know what it needs, and then whether or not it's strong enough to get exactly what it wants. So in the example of calcium and chlorine, what we've been doing is we've been going to the periodic table. So let's see if I can go to that. We've been heading to the periodic table, and let's say for chlorine, we find chlorine over here, and we see that it has, this box right here is chlorine, and we see that its atomic number is 17. So that means it has 17 protons and 17 electrons as a neutral atom before it's interacted with anybody else. So we know that chlorine's atomic number is 17. Oops, didn't mean to do that. So if we go back to our drawing here, erase this, make that go away. We've got chlorine, for God's sake, Sarah. Chlorine has the atomic number 17, so we know that it's going to start putting its electrons in its shell, and we can fit 2 electrons in that innermost shell, but chlorine has a total of 17 electrons, so we've got 2 there, 3, 4, 5, 6, 7, 8, 9, 10, and then I have another 7 that I have to account for, right? 1, 2, 3, 4, 5, 6, 7. So that's what chlorine looks like when it's born into the universe. And it's got a problem because it wants a full valence shell of electrons. And so it's going to need to find some way to go about filling that outermost shell. So at the moment, we've got this problem where we've got this vacancy here. We've got a spot available for 1 more electron. So chlorine is going to work very hard to try to get that last electron. So we can actually erase these inner electron shells just to clarify what's going on here. And so you can see in the outermost shell, which is the one we're concerned about when it comes to whether something is going to bond or not, you can see that it's got 1, 2, 3, 4, 5, 6, 7 electrons. So if we kind of erase, just getting the hang of this, folks. We can simplify this even further, so we can look at what the very simplified scenario is for chlorine. And that is, we can draw it this way. We do 1, for God's sake, 2, 3, 4, okay. So we can draw chlorine like this, and this is called a Lewis dot diagram. So it's simplifying this diagram down so that we're showing only the electrons in the outermost shell for chlorine. So we've got 1, 2, 3, 4, 5, 6, 7 electrons in the outer shell. And that means chlorine is on the lookout for 1 additional electron, right? So then we have the potential partner of calcium also coming in. So if we were to look up calcium on our periodic table, we're going to see calcium is way over on the left in the second column, and it's got the number 20. Now, you can take a long time drawing all these atoms and saying, okay, the atomic number is 20, I need to draw all of its electrons and all the shells and figure out how many of everything there is. But I'm going to give you guys a little shortcut to tell you something rather important about the periodic table and how it can help you. So if you see, like let's say over here, we've got chlorine, and Chlorine has, we just determined, we drew chlorine from scratch, we built all of its electrons, we find out that in its outermost shell it's got 7 electrons, so it's got space for one more, so it's going to be questing for one more. And what you'll see here, it's kind of hard to notice it at first, but this number 7A at the top of the column that chlorine is in, so the top of this column has the designation 7A. So what that 7A designation is it's a shorthand way for you to look at the periodic table, find a particular element that you're interested in this case it's chlorine, and by looking at that number at the top of the column that it's in, you'll know how many valence electrons it has, so how many electrons are in that outermost shell. So instead of having to build every atom from scratch and figuring out how many electrons are in the outer shell, you can just say, oh, chlorine 7A, group 7A, that means it has 7 valence electrons, it's going to be on the lookout for one more. And you can do that with any of the columns that have an A designation. So you can see 1A over here, 2A here, and then we jump to 3A, 4A, 5A. So this whole section in the middle, you can't use the rule. So can't use this rule for that. But for any of the elements that fall in one of those columns with an A designation at the top of it, you can use that there. So I'll just take those away. So that means if you're interested in calcium, so we find calcium here, this box right here, and you could build it from scratch. You could say it's got 20 protons, so it has to have 20 electrons when it's born, and I'm going to draw all these pictures of it and everything. Or you can just look at the fact that it's in this column, and this column has these designations at the top, and you can see 2A is listed. So what that means is that calcium has 2 valence electrons. So that's the situation that it is in. So we can go back to our whiteboard here. Erase this. Good God. Someday I'll understand this. So now we've got a shorthand way of looking at these things very quickly. And we can say, all right, so we looked up chlorine, and it was in group 7A. So we'll go 6, 7. So that means it has 7 valence electrons. And then calcium was in group 2A, which means it has 1, 2 electrons. Right? So these are called Lewis dot structures, and they tell us how many electrons an atom already has in its outermost shell, and that's going to tell you how many it needs in its outermost shell. So chlorine needs 1 electron. Calcium, on the other hand, has 2 electrons in its outermost shell. So it has kind of 2 potential things that it could do. It could find a way to gather up 6 additional electrons in its outermost shell, or it could potentially find somebody to take those 2 electrons that it does have off its hands, and that might solve its problem. So we can kind of think of calcium as wanting to get rid of 2 electrons. So now we know what each one of them needs. The other thing we're going to have to find out is how strong each one of them is. So we need to know the electronegativity for each one. So we're going to have to look those guys up. And our electronegativity, let's see, for calcium, So if we look up calcium, calcium has an electronegativity of 1.0, and chlorine has an electronegativity of 3.0. So we've got calcium electronegativity of 1.0, chlorine electronegativity of 3.0. So what we need to know is what's the difference between the two. So the difference in electronegativity here equals 2.0. And when we look up our rules on the PowerPoint, it tells us that if the electronegativity difference is greater than 1.9, then you're going to have an ionic bond. So if we have 2.0, that's definitely greater than 1.9. So that means when calcium and chlorine meet, they're going to form an ionic bond, because that's what the rules tell us. So, but what we have to figure out is what that actually would mean for when these two things come together and how we would draw those bonds. All right, so let's take an example where you guys were asked to do Lewis dot structures for NH3, which is ammonia. So you have to figure out, how would those atoms come together? How would they each get what they need? And what kind of bond would form between them? So we can use these Lewis dot structures, and we can use our shorthand for different things to figure out what they're going to do. So if you were to look up nitrogen on your periodic table, you'd find that it's in column 5A. So that means for nitrogen, we're going to have 1, 2, 3, 4, 5. So that's our quick kind of sneaky way of doing this, where we look at the periodic table. If we find that an element is in one of those A columns, then whatever number comes in front of that A tells you quickly, without having to build the whole atom, how many electrons are in that outermost shell. So nitrogen is in group 5A. That means it has 5 electrons in its outer shell. So this is its situation starting out. And then we've got hydrogen. So here's one hydrogen, and it's got 1 electron. So hydrogen is in group 1A, which means each hydrogen has only 1 electron of its own. So each hydrogen is going to look something like this. So our Lewis dot diagrams are really pared down, simplified ways of looking at an atom that shows you just the symbol for the atom and how many valence electrons it has, how many electrons in its outermost shell. So now you can see the situation kind of clearly in terms of what each atom needs. So we've got nitrogen here in the middle. Nitrogen's got 5 valence electrons currently, so that means it needs 5, 6, 7, 8. It needs 3 more electrons in order to fill its outermost shell. So nitrogen needs 3 electrons. Now each hydrogen has 1 electron currently, and since hydrogen only has that innermost small shell, hydrogen is going to have a nice full shell and be happy when it has 2 electrons in that innermost shell. So each hydrogen needs 1 electron. Now we have to figure out, so since every atom is always out for itself, and it will steal electrons if it can, we have to figure out if the nitrogen and the hydrogens do come together, is one of them going to be able to steal an electron from another one, or are they going to have to share them? And the way that we determine that is by knowing the electronegativities. So nitrogen's electronegativity is 3.0. Hydrogen's electronegativity is 2.1. So if you look at the difference between them, you're going to get, so if we subtract those, you're going to get, oh god, math phobia. Here we go, a difference of 0.9. So our difference in electronegativity equals 0.9. Now that, according to our rules in our PowerPoint, is not a big enough difference for nitrogen to steal an electron from hydrogen. So even though nitrogen is stronger, it's got a 3.0 electronegativity, it's not strong enough versus hydrogen, which is at 2.1, to steal an electron from it. So that means nitrogen and hydrogen are going to have to share electrons. So what we're going to see is we'll see sharing of these electrons like this. So hydrogen is going to be sharing an electron with nitrogen, and so what we see is this nitrogen in the middle, even though it came into the party with only 1, 2, 3, 4, 5 electrons of its own, now it's able to access an additional one that this hydrogen brought, an additional one that this hydrogen brought, and an additional one that this hydrogen brought. So when we tally up how many electrons nitrogen has, we've got 1, 2, 3, 4, 5, 6, 7, and 8. So that's a full shell. So nitrogen's really happy now. Nitrogen has exactly what it needs, and when you tally up the hydrogens as well, they each have what they need too. So each hydrogen came in with 1 electron of its own, and now it's sharing an additional one of nitrogen's. So all of these, what these are going to be, is these are covalent bonds. And that's determined because in this example, nitrogen is not strong enough to be able to steal from hydrogen, because they're fairly equally matched. Nitrogen is a bit stronger, but not strong enough to strip an electron away from hydrogen, and that means their only option is to interact and share. And then when you look at our rules in the PowerPoint, it tells us that when you're looking at a bond where electrons are being shared, so you're looking at a covalent bond, you have to then decide, am I looking at a polar covalent bond or a non-polar covalent bond? So a non-polar covalent bond is going to be one where the electrons are shared either exactly equally between the two atoms or just about equally. And the cutoff for that is if your difference in electronegativity is less than 0.5, then you've got a non-polar covalent. Now, in this case, we've got a difference of 0.9. So that's bigger than 0.5. So it's not a big enough difference for an ionic bond to happen. So nitrogen isn't able to steal electrons from hydrogen. But it is strong enough where it's not an equal sharing. So your electrons are going to spend more time circling around nitrogen. So they're going to spend a lot of time around here, and then an occasional loop around hydrogen. But most of the time they're going to be around here. So that's the nature of the bonds between nitrogen and hydrogen. They are polar covalent bonds. So these are the steps you're going to need to be able to do when you're looking at two atoms coming together. You need to be able to draw that Lewis dot diagram, show how many valence electrons each atom has. That's going to tell you what each atom still needs in order to be satisfied and get to that full outer shell, full valence. Then once you know what each atom needs, you got to figure out who's stronger. Are they strong enough to steal? If they're strong enough to steal, then you're looking at an ionic bond. If they're not strong enough to steal, then they're going to have to do a covalent bond. And once you know it's a covalent bond, you got to decide how equal is the sharing. So you'll look at your rules and figure out, are the electrons going to spend most of their time around one atom and not so much around the other, or are they going to be fairly equally shared back and forth? So that's how you approach these problems. You need to get comfortable with all those steps. Please do use that shortcut of when you're trying to draw one of those Lewis dot diagrams and figure out how many valence electrons an atom is starting out with. Use your periodic table. If an element is in one of those A designated columns, 1A, 2A, 3A, 4A, 5A, etc., use that to tell you how many valence electrons does it start with, and then you can draw your Lewis dot diagram that way.